I'm going to start recording now. Excuse me. I'm going to review some of the things that I did yesterday because I went through a lot of material, some of it very important and fairly quickly. So let's see, I think I'll make this a little bit bigger. Well, I don't need to make it that big, actually. Okay, so analytic functions. First of all, we're talking about a function, f of z, that's a complex valued function of a complex variable. So in other words, we're talking about z, wow, z equal to, let us say, x plus iy. That's what we typically say. And f of z then is going to be a real part plus an imaginary part. And I sometimes wrote them as u of xy plus iv of xy, or equivalently, u of z plus I v of z. So I'm being a little sloppy with the notation here. So let me clean it up just a little bit. And the important thing here is that the derivative should exist no matter how. In other words, f prime, which is at, say, z0, which is f of z minus f of z0 over z minus z0. This limit should exist no matter how z approaches z0. So z could go like that, or z could go like this, or z could come in like this, or z could come around and go like that. So no matter how z approaches z0, this limit here, this limit has to exist and be unique. Then we say that the function is the function is differentiable at z0. Let me just clean this up a tad here. It's somehow when I'm writing, if I put my hand on the iPad, sometimes the iPad takes that as an instruction and does something. And so I'm reluctant to put my hand on the pad. In other words, on the other hand, if I don't put my hand on the pad, then and try to write without putting my hand on the pad, the writing is terrible. Now, if the function is, let us say, differentiable in a region about some point z0. So it's differentiable throughout this whole region. Then a small disk, in other words, about z0, then it's said to be analytic. Whoops. So this is Jesus Christ. So then it's said to be analytic at Z0 and inside the disk. So that's basic. Those are basically the definition of what we mean by analytic. That is to say, if it's differentiable throughout a small disk, then it's analytic in that disk. And differentiable at a particular point means that this limit here exists no matter how z approaches z0. Now, in particular, the polynomials are differentiable, and you can see that here that the difference between f of z prime and f of z is approximately n z to the n minus 1 dz, and so the dz's cancel, and we have a nice derivative. A function that's analytic everywhere is said to be entire, and all the polynomials are entire functions. Now, it's important to be able to test whether a function of x and y is in fact an analytic function of z. And it's not always the case. For example, x squared plus y squared is not analytic. And there are more functions that are not, most functions of x and y are not analytic. The analytic ones are very special. And the conditions that an analytic function must satisfy are called the Cauchy-Riemann conditions, or Cauchy-Riemann conditions. So we have two different languages working here. And they follow from the definition of analyticity, namely that the change in the function, we have a function of x and y, so the change in the function, so let me try writing in red, let us say, the change in f of x and y, well, this is the change in u of x and y, plus I, the change in v of x and y. Here I'm saying that f is u plus iv. And so this change in u is the partial, let me use subscript notation so I can do this quickly. This is the partial derivative of u with respect to x times dx plus u sub y times dy plus I v sub x dx plus I v sub y dy. And we want that to be not any old complex number, but in fact proportional to dx plus I dy. So in other words, this has to be f prime of z, or x and y, times dz. In other words, it has to be f prime of z times dx plus I dy. And so that means that we have this equation here, which I've just written in a somewhat different way. And so if we look at the parts dx and dy, we have here a dx part, and here a dx part, and here a dx part. And so this is saying that u sub x plus I v sub x dx should be f prime dx. And which, of course, is just another way of saying that that u sub x plus I v sub x is f prime, and the dy's, well, these are saying that u sub y u sub y plus I v sub y should be equal to the coefficient of dy then is I f prime. And so that tells us then that, I hope I've got all the subscripts right, that u sub x plus I v sub x times I should equal u sub y plus I v sub y. And so this is then minus v sub x is u sub y, and u sub x is v sub y. And I hope these are the conditions over here. U sub x is v sub y. That's this condition, which is this condition. And minus v sub x is u sub y is this condition over here. And so that is this condition. So that's where the Cauchy-Riemann conditions come from, and they let us tell what is an analytic function. And and so we can say these are the CR conditions. And that's how you tell if a function is analytic. And here are some examples. And as I said to you a moment ago, most functions are not analytic. Analytic functions are very, very special. In the space of functions, they're a space of lower dimension than the whole space of functions. And you can think of them as a set of measures zero, which is a sort of fancy way of saying it, possibly a meaningless way of saying it, but anyway, that's beside the point. Here's a function, f of z is 1 over z minus z0. That's a function that's infinite when z is equal to z0. So it's not well defined there. It's not analytic there. Well, it's well defined, but not analytic there. But it's analytic everywhere else. And one of the important consequences of analyticity is something called Kaushi's integral theorem. And so if I draw a little line here, the Cauchy-Riemann conditions imply the integral of a function along a closed contour. That is to say, one that doesn't go anywhere, a loop, in other words, of some kind. Vanishes if the function is analytic on the contour and everywhere inside it. And so what I did last time was I went through in some detail the computation of the integral along the four sides of a rectangle. And I picked a rectangle that happened to lie on the real, on the imaginary and real axes. And so it went a distance L. This was L, and this distance here, this point here was H. And I went through that in some detail, and the assumption here was that we were integrating f of x, x and y, and we were integrating dx plus I dy. That's what dz is. But along this leg here, we just have dx, and then along this leg here, we just have dy. So this is, so here it's dy, and over here it's dx. And we start at the origin and we end up at the origin. And one can do that integral exactly, well, formally exactly, and it turns out to be such that the real part, of this integral around the rectangle of f of z dz, this turned out to be this expression here, and it was, in other words, minus an integral 0 to L, 0 to H, and it was u sub y plus v sub x dy dx. And by the Cauchy-Riemann conditions, that's 0, or it's 0 if the function is analytic. And we found that the imaginary part of this integral was over here. It was again integral 0 to L, integral 0 to H. And now it was minus v sub y plus u sub x dy dx. And by the Cauchy-Riemann conditions, that's 0. So that shows you that an integral around a rectangle, as long as you're in a region of analyticity, you've got the Cauchy-Riemann conditions holding, and so that integral vanishes. And this, in fact, then is effectively an area integral. We're integrating over the area. In both cases, we're integrating over the area here of the inside the rectangle. That's what dx dy or dy dx is. And now that in a sense, this example really tells us everything. I did several examples in this section because I thought this material was so important. And as I said to you before many times, complex variable theory is such that when you define what analyticity is, everything else follows. And in particular, in this case, now that we know that the integral around a rectangle of an analytic function, as long as the rectangle lies, the rectangle and what's inside the rectangle lies inside the region of analyticity of the function, that integral around the rectangle vanishes. And so what we have is that I'm going to undo that. The integral along of the rectangle f of z dz equals 0. That is to say, if f analytic inside rectangle R and inside and on rectangle R. And of course, normally what we can say is that we simply have a region of analyticity, and we're doing a closed integral around a rectangle. It's automatically zero, and that's true no matter where the rectangle is or how big it is, as long as it's within a region of analyticity. And then what you can do is you can put a bunch of these rectangles together, and the rectangle, the line integrals along, the line integrals that are in opposite direction along the same line cancel. And so we have here red and blue canceling, and then over here we might have another rectangle, and here we'd be going down, and so these two would cancel, the blue and the red, the blue and the green. And so what happens is all the interior, let's do a big rectangle so we use up a lot of this volume. Then we're going down there, and all these guys cancel, these guys cancel. And so what we're left with at this point is just this integral. And as we add more rectangles of appropriate size, everything cancels on the inside except for the integral around this loop, or equivalently, we pick any contour inside, we can arrange that everything vanishes. All the line integrals vanish except the line integral, the outer line integral, and that one therefore vanishes. And so the result is that integral f of z dz equals 0 as long as C is inside a region of analyticity. And by inside, I mean it's, totally inside, and moreover that that R has no holes. In other words, it's a simply connected region of analyticity. Again, looks like Swiss cheese. I'm sorry, it looks like American cheese, not Swiss cheese. So the region has to be something like this, and it has to be, whoops, I hit the wrong thing. The whole region has to be analytic, and like that. And so then if we switch to say red, we can have a contour in here, and the integral along that contour, we call that contour C, the integral along C, closed, circle meaning closed, f of z dz equals 0. So that's Kaushi's integral theorem. The integral of a function along a closed contour vanishes if the function is analytic on the contour and at every point inside it. A closed contour, of course, is just basically a loop. So closed contour equals loop. And I think I should have used that term instead of closed contour. But in all the books, it's always closed contour. And we want the region to be, so to speak, simply connected, because if we have a region that is in other words, suppose we have a region like this, and we can say, well, it's we have analyticity everywhere, but not, whoops, that inside here we have some singularities. So then we have a problem that if we actually try to do an integral like this, then the integral of an analytic function along a closed contour, that would vanish. But if we go around like this, and now we've got singularities inside, that one is not going to equal 0. So we call this C prime integral f c equals dz equals 0, integral C prime f dz not equal to 0. So that's basically the situation. So that's Kaushi's integral theorem. And one conclusion of this is that, again, if we have a region of analyticity, and we go from one point here, Z1 to Z2, then we can imagine integrating this way. Or we could imagine, let me do green, I think, taking a curve like that. And since this, if the function's analytic within that blue line, then the integral, let me try to say it in a, right, okay. Integral along the contour, the black contour, Jesus. Of well, let me stay with blue, I guess. F of z dz will equal the integral along the green contour. I don't know. Somebody maybe understands why it is that it keeps switching to so C prime. This is C prime, and this is C. I meant that to be blue, but never mind. Anyway, like, all right, let me make this blue. I can't imagine anybody's confused, but just in case. So these two contour integrals are equal, and the reason is that that the integral of f of z dz of c minus c prime is an integral that's a closed integral, and it is an integral that goes, let me do it in yellow, say, it goes up here like this, and then it comes down like that. That's the integral. That's a closed integral. That's a loop integral in the domain of analyticity, and so that is going to vanish. And what does that mean? Well, this thing here is equal to the contour integral of f of z. Let me just fix that. Minus the contour integral along c of f of z dz. And that, as we say, is equal to 0. So that means that the integral along c of f of z dz is equal to the integral along c prime of f of z dz. And what I'm talking about here is two different contours starting at the same points and ending at the same different point are equal. So I can draw the thing again. We've got here a region of analytic. I wanted to make that black. Region of analyticity. We have, let us say, a contour here, and then we have another contour there. And so if I want to do this in color, let me do it in color. Label the contours in color. And so this one is C, and this one is C prime, and so this is C prime, and this one is C. So these two integrals, line integrals, are the same. And that's stated here. In other words, a contour depends upon its endpoints and upon the function, but not upon the actual contour, as long as the contour stays within the region in which the function's analytic. And as the contour is deformed from one contour to another, or equivalently, we may continuously deform the contour of an integral of an analytic function from C to C prime without changing the value of the contour integral, as long as these contours and all the intermediate contours lie entirely within the region R and have the same fixed endpoint. So this is the theorem. I guess that's one version of Kaushi's integral theorem. And I see here I have a typo, so let me see if I can fix this on the fly. Yes, there's an extra as there. And is that's let me see if I can. Yeah, it's in the, I don't know if it made it into the book, but I'm going to take it out of the text in any case. Okay. So another way of stating Cauchy's integral theorem is the contour integral of a function along a closed contour lying entirely within the domain of analyticity of the function vanishes as long as the function is analytic at all points within the contour. All right, one way of seeing that for a polynomial is that the closed line integral of a polynomial is d, it's z to the n dz, but that's dz n plus 1 over n plus 1, and that just gives us z0 to the n plus 1 minus z0 to the n plus 1, which vanishes automatically. Okay, now the next topic is Cauchy's integral formula, and we just barely got to this last time. And the key thing is to do so let me switch now to a slightly different topic. Imagine that we're integrating a tiny circle, radius epsilon, of f of z over z minus z0 dz. And what one can see then is that what you do is you expand the numerator here. You say, well, this is just an integral of f of z0 plus I f prime of z0 over, again, z minus z0 times dz, and dz here is very simple. Namely, we have here z is equal to epsilon e to the I theta. So dz is I epsilon e to the I theta d theta. And z is not equal to that. Z minus z0 is equal to this. So z minus z0 is that. dz is I epsilon e to the I theta d theta. And so this integral then is equal to integral 0 to 2 pi f of z0 plus I f I think I went, it's I f of z0 times, so let me just switch here. All right, I'm going to have to fix this. This needs to be multiplied by, Jesus, multiplied by z minus z0. And then all of that is dz. And so this is f of z0 plus I f of z0. And that was wrong also. Z minus z0 is epsilon e to the I theta. And now all of that is multiplied by dz, which is I epsilon e to the I theta d theta. And then we divide by z minus z0, which is epsilon e to the I theta. And so now this cancels. These things cancel, and we just have a d theta integration. And so the first term gives us 2 pi I f of z0. On the other hand, e to the I theta integrated integral 0 to 2 pi e to the I theta d theta is just 0. So this term here does not contribute. And so what we wind up with then is a miniature version of Cauchy's integral formula. In other words, f of z0 dividing by 2 pi I, we have f of z0 is 1 over 2 pi I, loop integral around z0, radius epsilon, f of z, z minus z0, dz. Okay. So this is a miniature version of Cauchy's integral formula, but in fact, that's all we need to get the general formula. And the idea then is to do a contour like this. And a contour like that is 0. So in other words, what we're doing here is we're going to, so let me switch to blue maybe. So we have, if we follow this crazy contour, which is and let me patch this up just a little bit here. So in here we have z0, and we're going to do an integral along a contour, which we're going to call C prime. In fact, let me do that instead in blue. And so what do we have? And we imagine that we're inside a region of analyticity. So this is a region of analyticity. Hello, Sam. It's too early to go on, but soon. Region of analyticity. Okay. So this integral then, let me change colors, black maybe. Integral along C prime f of z dz over z minus z0. This is a closed integral, and it has no singularity inside it because you see this z0 isn't inside z prime c prime. In other words, we can take c prime and we could gradually deform it so that instead of being what we just wrote, we can say, well, it's the same curve except that over here it just does this. So if we can deform the contour C prime into something called, say, C double prime, and that integral f of z dz over z minus z0 along C double prime, well, that doesn't involve the singularity at z minus z. So in other words, the function f that's analytic throughout the domain of analyticity, but f of z over z minus z0 is analytic everywhere except at z0. And so if we design a contour, let me now go to, say, a yellow contour. Oh, damn it. Somebody may know why it is that, so here's a yellow contour that just does that. Well, obviously this integral along the yellow contour, which I can say is C triple prime. That integral is obviously zero because it's an integral that's of a function that's completely analytic, along C triple prime and inside C triple prime. But the same thing is true for these other ones because you can just, because they don't actually, because you can deform them continuously from C prime to C double prime to C triple prime in such a way that they completely bypass the singularity, and the deformations of the contour are deformations that don't leave the domain of analyticity. So what we then say is, well, what is this funny contour? Well, this funny contour along C prime is actually equal to, in fact, all right, I'm going to leave out the 2 pi i's. It's actually equal to the integral around C of f of z over z minus z0 dz minus the integral of f of z dz over z minus z0 along a contour that we called epsilon. Now, what is this contour C? The contour C is, so C is a contour, let me just draw it. So the contour C is, let me draw it in what color? Black, maybe. The contour C looks like this. It just goes around like that. So it includes the point z minus z0. But that contour, in other words, you see what's happening here is that these two lines here, one of them going this way and the other one going that way, but almost overlapping in the limit where the lines are the same line, they completely cancel. And so the integral just looping around Z0, that's the contour C, and that contour C is the so all right, let's try to look at this. So the contour C prime is this. So that's C prime. And what we're saying is that that is C minus a tiny contour like that, which is counterclockwise. Remember, this one is clockwise. It's counterclockwise here, but it's clockwise there. And the reason for that is that C prime, Jesus Christ, why does it keep switching? So this thing is equal to that. It's equal to the sum of those two. And this one is minus that one. So that's equal to and I hope those pictures are clear. In any event, the upshot is that the integral around C is the integral around the so in other words, the final answer here is that the integral f of z over z minus z0 around C is equal to the integral, the epsilon integral of f of z over z minus z0 dz dz, which is 2 pi I f of z0. So that's the upshot. And so we get Kaushi's integral formula, which is this one here, that f of z f of z0. I don't know what is going on. Integral of f of z0. Oh, why does it keep going? It keeps going blank on me. Over z minus, look at that. Z minus is 2 pi I. Apparently, I have to write very slowly. Well, this is getting very tiresome, having to use this pen in this crazy way. Let me see, is it running out of, no, it's 94% charged, so I just have no idea what's going on. Okay, so that's Cauchy's integral formula, and it's extremely useful. It's used all the time in complex variable theory. The two workhorses of, oh, I can't even get it to move. The two workhorses of complex variable theory are this equation, Cauchy's integral formula, and Cauchy's integral theorem, which is that this is just equal to 0. These are the basic theorems that are used all the time in complex variable theory. Well, we're essentially out of time. I'm going to stop sharing. God, did I forget to start a chat thing here? I did. Oh, well. All right, I'm going to stop.